Greetings from IIT Kanpur. Hope all of you are having a good day. So, let us continue our discussions on unit processes in the context of semiconductor processing and IC fabrication. We have already seen about thermal oxidation, how to grow in situ oxide on crystalline silicon, and we had a few lectures on that. Now, we will continue our discussion on diffusion. Next, another unit process, diffusion. Diffusion, it turns out, is a very fundamental phenomenon, and we'll see how we are using it in the context of VLSI processing, semiconductor device processing, and VLSI fabrication. So let's start off. So this is diffusion. This is the first lecture that I'll be telling about diffusion. First, the disclaimer. So this is a broad overview of the diffusion discussion. So diffusion, we will talk in the context, of course, of device processing, and we will be reviewing the following sections. There will be 3 lectures. In lecture 1, we will talk about diffusion in device processing, where all we are likely to encounter some very brief introduction here. Then we will go into the basic model of diffusion, the very physics of it, how diffusion takes place, how do you model it mathematically. Then we will talk about diffusivity value in different materials, especially silicon and silicon dioxide, various materials, how they diffuse in these materials, in silicon as well as silicon dioxide. Then on lecture 2, we will talk about standard solutions of diffusion equation and thermal doping of silicon by thermal diffusion process. Then we will, in part 3, we will go a little deeper, higher level concept on thermal budget, very useful concept. As you will realize, this is what helps us keep track of what happens in subsequent processes as what we have done in previous processes. Then we will talk about different types of thermal diffusion mechanisms. May not be exhaustive, but at least an inkling of what are the popular things that we have to watch out for, and some anomalous diffusion effects. So it's a 3-part lecture that we will have on diffusion. So let's start off with part 1. So part 1, we will talk about diffusion in the context of device processing. As in the earlier some of the earlier lectures, the 3 texts, any 3 you can follow, or you can even follow some other texts, because this topic is covered by many authors. The books by Z, Gandhi, and Wolf and Tauber. Okay. But there's also another interesting book which I thought gives some very good insights, Electronic Thin Film Science for Electrical Engineers and Material Scientists by Tu, Mayer, and Feldman. I will be using some material from that book during this discussion. And if you are in a position to do so, you may want to check for this online. But this is a little advanced topic, what they are discussing. I will discuss what is pertinent to us immediately as beginners in semiconductor processing. So this is the outline of the first part of the first lecture that we are having right now, diffusion in device processing. First, I will talk about relevance of diffusion, especially in device processing, why we need to talk about it, why make a big hue and cry of it, make it even a unit process. Second, I would talk about the diffusion phenomena, the mathematical concept, and then I would talk about some representative examples of processes that involve diffusion processes. So where does one encounter diffusion? If you look at it, whenever temperature is greater than 0, you are likely to encounter diffusion. It is a very fundamental phenomenon. Actually, as long as there are many particles around, diffusion comes into play. So it's not something that you want or don't want, it happens. Okay. And many of you must have studied in your school about Brownian motion, ink spreading in water, perfume smell. If it is in one corner, you have some perfume bottle open and somehow the whole room smells, spread of weeds in a field, see the diverse activity, and then spread of population of tigers in a forest. If you release a few tigers in one corner of the forest, and how they as the number of tigers increases, how they spread across the forest, there is an element of diffusion involved in that. Okay. So in order to just emphasize this importance of this, let me talk about one example. So we have here a glass of water which is at room temperature. Okay. So what I'm going to do now is I'm going to put a little bit of ink inside it. Let's see what happens. What do you find? You find that the ink has higher density, so it is slowly going down. But what is also interesting is it is not going down by itself, it's going in all directions, if you notice carefully. And what is that? That is diffusion. Essentially, the ink molecules are agitated, so are the molecules all around in the water, and they are making it move all around. So as you can see, it is diffusing slowly. Now what I am going to do now is, I am going to do the same thing with hot water. Let us see how it works. This water is around 80 to 90 degrees centigrade. And I'll put the same ink in this. So let's see how it moves. What do you find? Immediately it moves in all directions. Here too, of course, it is trying to go down, but you can see it immediately moves all around. And this is another facet of diffusion, that when you go to higher temperatures, you have a marked increase in the number of diffusion. So let us now put them together and see, compare them.
We see that the ink in cold water has not yet completely diffused. On the other hand, the ink in hot water has completely diffused.
The ink in hot water is completely diffused. Why is that so? That's because diffusion constant has gone up. Diffusion constant is exponentially dependent on temperature, and even a 50 to 60 degree change in temperature, you can see there is a big difference in the diffusion constant. So this is precisely what we will be using in the diffusion of dopants in our semiconductors. So what did we see now? We saw that even at room temperature, when ink comes in water, it is spreading in the horizontal direction. Vertical direction was mainly because of gravity, but water molecules are bombarding on it, and the ink molecules are also agitating. Some are going to the left, some are going to the right, and eventually they spread out. And if I let it go, as we found towards the end of the demonstration, even in the cold water it had spread significantly. Of course, a lot of them settled at the bottom, but they spread through the thing. It had a bluish tinge. What did we see when the temperature was raised? Very rapidly the ink spread. That means diffusion rate goes up significantly at higher temperatures. So this is a very fundamental idea, and we saw that with the help of ink. It is this concept that we often end up using, especially in the context of semiconductor devices also. So let's continue our discussion on that. So we use diffusion process. Actually, we have used it significantly in the past to build ICs. And there is need to understand this diffusion process as a unit process, because of not just because we are building it, not just because we are building the device, but even when the device has been built, the various other phenomena that where diffusion just kicks in. And if we don't understand it properly, we will be in trouble, because what we predict is not what is happening, because diffusion has modified things and rearranged things around. So let's continue and see how that is so. So how do we use diffusion to build devices? We look at these points a little bit closely. So we perspicaciously use diffusion process to build ICs. Very smartly we use it such that at high temperatures we make molecules and atomic species to move. At high temperatures we bring in molecules together and then allow diffusion process to take over and make it move. And since the process is well understood, we can predict very exactly where it is going to move. But once it has moved where we wanted the molecules to move, what we do? We decrease the temperature and freeze the atomic species during the actual device use. That is, the fabrication will be done at an elevated temperature, and then once the molecules are moved to the right place, we quickly bring down the temperature to room temperature, which is where the device is going to work. So that means we have frozen the molecules where they are, because as we saw, high temperatures molecules move fast, low temperatures they move much more sluggishly. And it turns out at room temperatures they hardly move in the case of many of the impurities in silicon. Not all, but some of them don't move at all. So this particular trick that was done, most of the processing was done at a higher temperature, where very often we use the diffusion process itself. Of course, we use higher temperature to do other things like oxidation and all that we saw, but we use diffusion process itself to form p and n regions, that is by doping of the semiconductors. So one of the primary uses of diffusion as a unit process traditionally has been to dope the silicon either as an n type or a p type by bringing in boron or phosphorus or arsenic or antimony and allow it to diffuse and to form the p region or the n region respectively. Okay, so this is the key thing. So I'm going to show this a little bit with schematically. So if you look at it, what we do is initially we have the silicon wafer, we make an opening in that, and at the opening we bring in the species we want to diffuse in the silicon. This invariably, this species is some dopant. So we have a what is known as pre-deposition, because what happens is this TH1 or elevated temperature of H1, what will happen is there will be, it will start, the species will start dissolving in the silicon. So there will be a solid solubility limit it will reach, and it will get dissolved in this region at T0 plus. But then we keep it at higher temperature, continue to keep it at higher temperature, so that some of these will also start diffusing into the silicon. After it has diffused in the silicon, and we know that we have got sufficient amount of material inside, sufficient amount of the dopant inside, because we want to make usually junctions, and we know how much of material we need to put to make a certain size of a PN junction, right? Once it is inside, according to plan, and actually there are many solutions in this, and this is where process integrators and process designers put in a lot of effort. You decide what temperature you want to take. So you take it to a different temperature. It could be the same temperature also, but you take it at a different temperature, but turn off the species that is coming, and you maybe you'll even remove the dissolved material here. So only the one that has diffused remains. Okay, and then what you do a drive-in, what they call a drive-in. You keep this at higher temperature for long enough time. Okay, T3 minus T2, a long enough time. And then what happens is the species that has diffused inside, that slowly comes out, and the junction that is formed is deeper and deeper. And you know how deep you want. And the beauty is we can predict this process so accurately that within a few nanometers or tens of nanometers, you can do it comfortably. And that was what was done in the earlier processes. Today, of course, we have much better control, and we can control it much more precisely. Of course, at some level, the statistics comes in, but we can control a lot. So what do? First, you have a high temperatures depending on how much material you want to get in, and then you bring the dopants, stop the dopants, and only have inert gas. Change the temperature if required, and then do a drive-in, and then it goes in. So once it has reached the particular depth, the dopants have reached the particular depth. Say you're creating N and P region, right? P substrate and N region. So phosphorus is coming in. Once you know amount of phosphorus has reached up to a particular depth, depending on the profile, and you can predict all this based on mathematical modeling, you do the next thing. You freeze it. That is, from high temperature, you bring it to room temperature. And if you do that, these molecules no longer move. As we saw in the case of the hot water and cold water, in the cold water, it was not moving much. Hot water, it was moving much more rapidly. So when you had higher temperatures, it was moving and diffusing, but at room temperature, it hardly moves. And luckily for us in silicon, as we will see later, the dopants don't move much at room temperature. And so we can actually make sure that they stay put there. You can actually visualize this also with a graph. So let's look at this graph. This is the concentration of the dopants, and x-axis is the depth. So this is the x-axis coming down from the top of the wafer. So if in this case, at pre-deposition, at the start T0 minus T0 plus, you have some amount of solid solubility material at this boundary. Then during the continuation of the pre-deposition, and you keep it at high temperature TH1, it diffuses through, and because the surface concentration is going to be solid solubility value, it remains there and it comes something like this. It takes a profile like this, and we'll see complementary error functions. That's the shape it takes. And then once you go to the third and fourth step, the drive-in, you remove this solid solubility value by etching it or removing it, and then you drive it in. And notice that the concentration value, the amount of material inside is constant, right? So this surface concentration actually drops, and it comes like this at some temperature T2 and at some temperature T3, and it comes like that. And once it is at T3 and you have completed the drive-in process, you freeze it and bring it to room temperature or the operating temperatures that you have, and this is how the profile will remain put. So what have we done? We know diffusion happens at high temperatures. We bring in species that we want, make them diffuse, because we know the mathematics of it and we are able to predict well. We know what temperatures and we need to take it and for how long we need to anneal it with the source, with the actual dopants being present at the surface. Then remove the dopants from the surface and do a drive-in. We know the total number of dopants that are inside. First order, they remain constant and they just go deeper and deeper inside by the same diffusion process. And then you bring it to lower temperature so that you freeze it. So this is the trick. You do processing at high temperatures, things move around, but you do it in a controlled manner, and when you want the thing to stop, you stop it and then bring it down. Okay, that's how whole VLSI processing has succeeded over the last several decades. So let's continue. We need doping by diffusion, yes, but nowadays there are other tricks to do doping, and we'll talk about that a little later. Ion implantation, that's become much more popular now for when you want to make an N region or P region, although you sometimes do have diffusion, especially for experiments and certain situations. You may use doping diffusion by thermally. But then there are other reasons why we need to know about the diffusion. So let's see why. It's as a background phenomena. The diffusion process and models are the core of different IC fabrication steps and processes. Whether we like it or not, we have to know it, and many times we have to know it in order to use that. So let's see two cases where we use it. Supposing you had an implant profile something like this. Somehow you managed to put it. We'll discuss more on this about this implant process later when we come to that implantation part discussions. So you have an implantation happening. Now if I do a high temperature anneal, I take it to higher temperature, what happens? The amount of dopants that are present, of course, are all trapped inside the silicon matrix or whatever that is. It could be silicon dioxide or whatever is there, it's trapped inside. And when you take it to high temperature, it starts diffusing and it spreads out. And this is one of the key things about diffusion, as we saw. Even in the case of ink, it spreads out. And again, of course, you bring it down to room temperature once you know where you want to stop. That's when you want to consciously do it. Sometimes when you have done this profile something like this, and then it turns out for some reason some other high temperature process is happening, say oxidation is happening. We know oxidation takes place at very high temperature, but somewhere else you have made some doping, that also will diffuse. So you better know when you do the oxidation high temperature process how these dopants will redistribute themselves. For that, we need to know about diffusion. We need to know the diffusion process and know it very accurately. So this can be a purposeful process, or this can be happening incidentally. If it happens incidentally, we need to plan for it, account for it, so we make sure that the subsequent processes that come in are at for a given time and of high temperature process, and the temperatures are controlled. There are also some situations where this diffusion process is part of a chain of processes. Okay, we have already seen a couple. I'll show that next. But before that, supposing you have molecular beam epitaxy, you'll have gases coming from the ambient, and then once a few molecules may interact with the substrate, and they may even react, or it may be just deposited. When they are deposited in an open flat plane, and they are not full already. So but what is interesting is they can actually move around. There is surface diffusion. There's a lot of surface diffusion out there. So when the surface diffusion happens, you can actually plan things such that the molecules are coming in a particular growing in a particular fashion, and there are tricks to do this. And also, whether you are planning things or not, whether you are intending to do it or not, it's good to know how the surface diffusion happens, so that what you predict about the whole MBE process, the chain of processes, your gases coming in, depositing, and then they have to form the crystalline form, right? So all that is there. So this surface migration and surface diffusion is part of a chain of processes, and for this we need to know about diffusion. Let's take some more examples of diffusion. Diffusion models are invoked to explain and understand aspects of variety of IC processes, and a couple of them which we have already seen. Let's see. First, when we talked about the Czochralski process, you might remember that we talked about how the dopants that are rejected are going to go into the rest of the silicon melt. This, the way and because there's a rejection of dopants here, the concentration of dopants will be higher at the edge of the silicon ingot where it is forming, and the liquid, the background doping. So there is clearly a gradient in concentration, and you will have diffusion. It's important to be able to understand and model this so as to come up with the expressions of what the effective segregation coefficient is, and other things that we just touched upon when we discussed this. So this is an example where you better know about the diffusion process and make sure you account for it if you want to understand the process and make use of whole process steps to get what you want or prevent what you don't want. Another example which we have already discussed is the oxidation, the previous unit process that we looked at. There we had talked about oxygen or oxidation species, maybe it could be water also, moist water vapor, high temperature water vapor. So you will find that there will be solid solubility, and then it will actually diffuse through the oxide this time. It's not diffusing through silicon, it's diffusing through oxide. It comes to the other silicon dioxide silicon interface, and this is where the reaction was taking place. So as you can see, it's a complex process of oxidation species coming from outside to the surface of the wafer, then diffusing through the dissolving in the oxide and diffusing through the oxide, and then reacting at the other end to form the growth of oxide. So clearly one of the key intermediate steps is diffusion process, and as we saw, diffusion limited if when it becomes your oxide thickness growth rate changes. So this is where the whole idea of knowing how the diffusion takes place is important, not just in silicon but also in silicon dioxide in this particular case. Okay, so I think it is clear to all of I'm sure all of us that diffusion process is something we can make use of, but whether we like it or not, it's also there in the background. Plus sometimes it's part of a chain of process that we design to do things. For example, it could be oxidation, or it could be uniformly doped silicon ingot. To understand how to get it, you need to account for this diffusion process. Okay, so what are the takeaways of this brief section? First, diffusion is a universal phenomenon, and as long as the temperature is above 0, there will be some diffusion. But of course, it's another matter how fast the diffusion is taking place. It can happen that the diffusion is so very slow, it can take several ages of the universe for you to see the effect. So that means you don't have to worry about it. And sometimes it need not be even as long as several ages of the universe. Even if it is several years, for a process that's happening over a few minutes, you don't have to worry about the diffusion process, right? So you can afford to ignore it as long as the diffusion rate is low. And this is why we need to know about diffusion, when to ignore, when not to ignore, and how to use it for what you want to do or what you want to avoid not doing. So use of diffusion process is needed for VLSI. Primarily, traditionally, it was for doping process that it was used, and people used to study this extensively at a time when doping by thermal diffusion was the primary way to get the N and P regions in a semiconductor. Now, if diffusion can be affected by various ways, and diffusion can play a role in various ways. So, redistribution of dopants during thermal annealing step is a key part. This is sometimes intended, as I mentioned, sometimes you have to account for it. If you are doing a high temperature process after you have made some diffusion profile, it will get disturbed by the high temperature process. So, if you did not account for it, you will be in trouble in your anticipation what is going to happen. So, you can actually plan these things, and we will see how to plan it. Surface migration in various process steps also is something that is part of a big step, and there are where you need to know about diffusion. And diffusion models actually helps us plan for various processes even within certain processes, and I'm just touched the tip of the iceberg. You may encounter this in many other situations in the semiconductor processing. So with that, we come to the second section of this lecture, where I would go into the physics and want to discuss about the basic model of diffusion. Here, as I mentioned in the start of this whole lecture itself, the three popular book for processing, and there are many other popular books as well, but I have mentioned here three. And then I'll also use the book material that is present in 2 Mayer and Feldman for bringing out some points. So let's get started. What I'm going to discuss in this particular section is the basic diffusion equation in a one-dimensional analysis. I want to make a disclaimer right away that this is not the universal way in which one can describe the diffusion, because there are always some nuances, there are always some parameters that come in which can be slightly different in various situations. Okay, but what I'm trying to bring to you is a simple way to understand how diffusion can be explained or modeled mathematically. What will change when you bring in the other parameters is the nature of the constants that come into the diffusion. You might have to bring in some modifications in that in order to account for the other variations that are there. But let's look at a simple basic one-dimensional analysis. Then I would like to go into one slightly more special case, which is what we normally encounter in our doping within silicon or silicon dioxide or in the solids, atomic diffusion in a crystalline solid, that is for silicon, and sometimes even for amorphous, but that will have some modifications again. But here I'll talk about crystalline solid and modeling of the diffusion constant in this case. I'll take information from 2 Mayer Feldman, who have explained it beautifully there, to how to find out what the diffusion constant is in certain conditions. So we'll start off with this diffusion in one dimension. Okay, in the real world, diffusion of course happens in 3 dimensions, right? But one dimension we will focus to get started. So supposing there is material in which the concentration of some particle is C of x is distributed in the way that is shown. So here I have shown a positive gradient of C, that is concentration of C increases as we go up in x. Okay. Now the reason diffusion happens is primarily because at temperatures above 0 you expect them to move around and vibrate around. There is of course a statistics involved in it. All particles will not vibrate at the same time in the same direction, but they will move in random ways with different amplitudes and magnitudes of oscillations. Sometimes they move around as well because of having energy, and they find that they can move there. Now what we will make an assumption is the particles in this particular case, and this is an assumption because it may not always be true. In fact, more often it is not true, but for a simple example we are taking this. At any point of time, any particle at one position will either move to the right or move to the left. In reality, as you can imagine, that's not the case. At any point of time, mostly it will be there, but a few may move to the right, few may move to the left. Of course, you can develop the model using that idea also and you'll get similar results, but for the sake of simplicity, let's assume that every particle at any instant will either move to the right or move to the left. Okay. So if that is the case, let's define a mean free path x plus delta x and x minus delta x to be the positions where the particle at x can move at any particular instant. So it will move either here or there. That's a mean free path. So notice that it's a mean free path. So statistically it can move less, it can move more, whatever. But here for simplicity again, we assume that let's only take the mean free path. Let's assume that everything moves either to the left, right, on an average whatever it moves, or whatever on average moves to the left. So what is the flux in any direction? It will be half of the thermal velocity. Thermal velocity is because the temperature is not zero, right? So it's moving one side or the other. So and it's a one-dimensional system. So half velocity, thermal velocity times the concentration at any one point. So all the particles either move left or right, but the velocity is half, the magnitude of the velocity or the speed is half VTH C of x at any point. So what happens at the point x? Half of them move to the left, half of them move to the right. So essentially nothing remains there from what was originally there. That's the assumption that I've made for simplicity. But let's assume that if that is the case, the particles that are present in this position, they will also move to the right and to the left, and similarly what is at this position will also move to the left and to the right. So if that is the case, the net flux that will happen is whatever is coming in from the left side and whatever is coming in from the right side. Okay. So and half of the particles that are present here are going left and half are going to the right, half are going to the left and half are going to the right. And the velocity of this of the ones that are coming from the left is to the right, which is positive in our convention, and the ones that are coming from the x plus delta x is negative, which is minus in our convention. So the net flux that you have, the way the particles are flowing at that instant, capital phi of x is half of the thermal velocity multiplied with the concentration at x minus delta x, and the concentration is x plus delta x. And this can be simplified by taking the common things outside in the bracket. Now what we do what is the fundamental thing which we always do, a Taylor expansion, and we do one more simplification. We usually go the first order expansion of the Taylor series. You can always go to the fifth order if you want, but many times it may not be of much use, especially when delta x is very small, right? So typically we go for the first order expansion. What is interesting is even the first order linear approximation itself gives us a wonderful insight into what is happening in this world. But this deviation sometimes that we see is also because we are just taking the first order. In that case, we'll have to take the second order or the third order approximation. But anyway, for the moment, let us take the first order expansion, Taylor expansion, what is inside the square bracket here. As all of you might remember from your first year college mathematics, Taylor expansion, phi of x is half of V thermal velocity, that is outside, and then C of x minus delta x is C of x minus delta x into the slope. This is the first order expansion, and on the right side will be Cx plus the slope. Okay. So now you can open up all the brackets and you can certain things cancel out. The C of x and C of x cancel out, and this has minus already here, and this is minus outside the bracket, so you have minus coming out here. And then what happens is you will have 2 times delta x times this value, and then you will get this expression. So this is what is it is leading us very close to what is very one of the popular understanding of diffusion. So what we do is we define VTH times delta x as capital D. If that is the case, phi of x is equal to minus D times the slope of the concentration. Note the important things here, the minus and the concentration. Higher the concentration variation, higher will be the flux. And the negative sign indicates that if the concentration is increasing, the flux is going to be in the opposite direction. Okay, important physics aspects, and we should always remember that. So essentially what it is meaning is it will flow from wherever is higher concentration to where is lower concentration, and statistically you can assume that there is a constant rate at which it is going, and that is proportional to d, and this d is equal to Vth times delta x. So we can actually put this equation that we got along with the rest of the information that we have. This is what is famously called Fick's first law. Now that we have understood this, let us bring in the continuity equation and explore further. We found that any concentration, any particles will flow from higher concentration to lower concentration. But let's understand this in terms of continuity equation and see whether we know at what rate they are changing, the profile changes. Okay, so this is taking off from what we discussed earlier. We have all the information here. So from continuity equation, what can you say? The rate at which the concentration changes, delta C of x and t, delta t, how does it change? It will change according to the divergence of the flux, the rate at which the flux is changing. If the flux is constant, what is coming in is going out, so nothing is going to change. Okay, so the rate at which the flux changes, negative of that, because it's going to go away, right? Flux is going away, plus generation minus recombination. In some situations you can have generation and recombination. For example, if you have light falling in, you have light generation, recombination of electron and hole. Such situations, generation recombination is important. Very often in the material diffusion processes and all that we discuss in processing, there is usually no generation and recombination in the volume that we consider. So if that is the case, we can make generation equal to recombination equal to 0. That's a special case of that. But if generation is equal to recombination, this equation boils down to delta C of x t delta t is equal to minus delta phi delta x. Now we know what phi is. We looked at it from the Fick's first law, so we can plug it in. So we can see delta C of x delta t is equal to minus of delta minus d delta C delta x whole thing delta divided by delta x. So what it means is the original flux that is there, the derivative of that, negative of that, and the original flux is d times the slope with a negative sign. This is what is known as Fick's second law. Okay. Now, why is this important? This tells how the concentration changes with time and how the concentration changes with space. It links both of them. So it's a very powerful equation which we often invoke in order to model what is happening. Okay. So first order, this is how diffusion takes place. So let's look at this Fick's law. So Fick's, just to reiterate, this was first proposed by Adolf Fick in 1855. Note, it's more than 1.5 centuries before, quite a long time ago. And it has stood the test of time, and it's a very convenient expression with which you can study about diffusion. And it's not just in semiconductor processing, but in a whole range of areas of human study, this equation can be invoked. Now we look at a special case, which is actually what is more popular. We saw that delta C of x delta t is equal to delta x of d delta C delta x, right? Now this d, diffusion constant, although it need not always be so, and in fact more often than not it is not so, but first order you can consider the d to be constant over the time in which we are operating. If it is constant over the time we are operating, as you know from calculus, the d can be brought outside the differential, and you have delta C delta t is equal to capital D times delta square C delta x square. So the curvature is linked in the space is linked to the derivative in time. This has a lot of repercussions, and we will see some of it also in the context of our organic in the concept of a semiconductor processing. And this is the more popular form of the equation, which probably you might have also encountered already. It's interesting that as t tends to infinity, what do we notice? As t tends to infinity, we find that this curvature will become flatter and flatter and flatter, and delta c delta t will tend to 0, and the curvature also will be flat, so there will be no curvature. So at t infinity, and if there is no curvature and no slope, essentially there will be no diffusion. So if you let things keep diffusing over time, they keep diffusing, and at some point they'll stop diffusing because there will be no slope left. Everything will flatten out. So even philosophically, some people believe that this is what would happen. Eventually, everything will come to nothingness, right? So it becomes flat. So it's very interesting that this equation captures this fundamental aspect of diffusion, and this is true for most of the processing that we do. If you do long enough, things become very flat, and the rate of diffusion also slows down, assuming that there are no other phenomena that is around. Okay, so that what we looked at was a simplistic model. It could be applied to a variety of places with a lot of approximations. If we tighten the model a little bit more, and we want to look at hopping of atoms over barriers, if we want to look at it, that's a way in which diffusion would happen, maybe in a crystalline material, or in fact in solids, although in the crystalline material the barriers will be periodic. So this could be one way in which we can visualize it. There is an atom which is sitting in a potential well. There are other atoms all around, and because of the placing of the other atoms, there is a potential well that is created, and this is sitting in the potential well A. And it's a periodic system. If it's a crystalline material, again that's one of the special cases. We see that there is a barrier which is delta Gm. Okay, maybe change the Gibbs free energy that is needed for it go from here to here, say. Now point A to point B, say the distance is lambda. So you could visualize this also as 2 points where the atom is going to go from point A to point B. It can be a distance of lambda. Of course, it can go to the left side too. There is nothing that's stopping it, but here I am just defining the thing. So there is a frequency by which it can go up. Similarly, if the particle were there, there is a frequency by which it can go up. Okay, so we can define the frequency of hopping from this to this, from one well to another. We can define that as nu, Greek letter nu, is equal to some nu naught, which depends on the material and the temperature and so on. First order, it is material dependent. Nu naught e to the power minus delta Gm by kT. Nu naught is a vibration frequency of the solid for those conditions, and delta Gm is the potential barrier for the hopping of atoms. Okay, so this is an interesting expression, and this is telling you what you're visualizing, that particles are hopping from one to the other. What is the way with which it is hopping? And hence we can see the delta Gm is the barrier. So the the probability of it going from here to here will depend on e to the power minus delta Gm by kT. Why? This is a Boltzmann's approximation, that the probability of this getting an energy higher than this is going to be this value, and if it goes higher than this, there's by a factor it will go there, and that factor can be included in this nu naught. So e to the power this is probability of the atom that it is going to go there. For dilute and ideal conditions, the B location is taken to be always empty, in the sense that if this is able to get its energy, this itself is the probability that it will go there. But on the other hand, that's not always true. If this is occupied, maybe it cannot go there. The space is not available. So those are special cases, and one can actually build models based on real life situations to model this and understand what is happening. But this is a simpler one of the simpler models, dilute ideal condition, where you have very few of these wells occupied, and in that condition how does it move. And this is very popular, especially when you are doing MBE, because when you start off, very few molecules are present, and how do they move around, and how do they coalesce at various places, and this is the way in which you model the MBE growth. Now this is when it is flat, right? If it is flat, this, if it moves here, this can move back also in the next step, or it can move to this. Okay, so it can move on both directions. But is there a preferred direction? That will require a chemical potential. So supposing the y-axis, the potential, there is a chemical potential in this direction, you find that because of this chemical potential, the barrier from here to here is the barrier that it will encounter to go from here to there is lower than the barrier from here to here, because of this slope by a value lambda times the slope of this potential energy variation, right? So there is a frequency nu plus and the frequency nu minus, and you can make simple models of this with using that exponential and get sine hyperbolic. It will be a difference of the two. So you can actually work with this. So the driving force in a sense is the slope that you have. Okay, mu is the chemical potential in this system for that atom. So for dilute ideal solution, we can write mu is equal to kT natural log of C, and we end up finding by very similar means that by expanding the sine hyperbolic to the first order, phi, the flux, is equal to minus d delta C delta x. Looks familiar? I hope it does, because we just discussed about it in the Fick's first law. And here notice, in this particular set of assumptions and all that, d ends up becoming nu times lambda square. Okay, it's a different setting. Okay, there we didn't worry about hopping and all that, we said it moves. But here we are talking of hopping with a frequency. So we are talking of nu times lambda would be the velocity. Nu times lambda would be having units of velocity, as you can see, and this is the velocity at which it is moving. And again, lambda will be the same. So VTH lambda we got earlier, it's nu times lambda. It's another way of looking at it, and this may be a good way of looking at it, because you can expand it to study how things move within crystalline material. And for those who are keen on going deeper on this topic, and it's a very fascinating topic, because you can model things and predict so well with the help of these, they are welcome to visit to Meyer and Feldman to get more ideas, so they can take their inquiry further. So now let's take a closer look at what this d is. We said it was nu lambda square, right? But let's take a closer look at it. What is this what is that nu? Okay, I won't be going into the details of how to derive it, although it is easily possible, and if you give some time to do that, and the textbook that I referred to is a good place to start. But let's get started. For modeling of real diffusion in solids, where it may not be so sparse. It's not that all places are empty and there is only one path. There can be multiple paths, because an atom is in a crystal in a three-dimensional world, right? So modeling of real diffusion in solid, the dilute ideal solution needs to be modified, right? So if you do that, you get this expression for d. D is the constant that we have, nu lambda square, right? So lambda square of course comes here also. So d is equal to f. F is the correlation factor, that is the tendency of it to go back to its place. There can be a reason why once it really comes, because of the history, it may want to go back to its place. So it is not that it will keep going forward. There is always a thing of calling back. So this correlation with the previous state, that f, is a factor 0 to 1. Then NC is the coordination factor. What is this? it tells how many nearest neighbor atoms are there. If I take an FCC structure, for example, there are 12 nearest neighbors, right? 3 planes. So you'll find there are 12 nearest neighbors. BCC, on the other hand, will have 8 nearest neighbors. What about silicon or gallium arsenide? Remember, it's a tetrahedral. There are 4 atoms which are the nearest neighbors. So the coordination factor here is 4. So notice here also we are considering only the first order coordination factor. You could go to second order, third order hopping also you can consider, although the probabilities are going to be low. But first order, again, it's already becoming complicated in a 3-dimensional world in a crystal, depending on how many coordination factor dependence one has to consider in the lattice. Nu naught is the vibration frequency of the solid. Okay. And what about these energies? Nu naught is multiplied by 2 factors. Remember that the entropy and enthalpy together would give you the entropy times times temperature, and enthalpy will together give you the Gibbs free energy, right? So that has been split up here. So you find delta S is the entropy factor and delta H is the enthalpy factor. Now there are 2 phenomena that has to be considered. One is the actual movement of the atom from one point to the other, and since we are not talking of a dilute ideal solution that it's always going to be empty, what is the possibility of that becoming empty? Okay, so we have to consider that. So F is the formation of vacancy phenomena. So 2 phenomena, one is the motion and one is the formation of vacancy. Combined, you have each accordingly you can determine what is the entropy and the enthalpy, and of course K and T are the standard variables that you have encountered, Boltzmann constant and absolute temperature. So this can be another way of identifying what the D is, and in fact material scientists have been doing excellent work on these, and they know a lot about how things move in atoms, and you can actually model them very precisely, and with modern computers it has become even more powerful way of predicting stuff. So in fact we actually can visualize what is happening and design things so that they diffuse in a particular way, or we prevent them from diffusing in a particular way, and so on. So this is fine. Those who are interested should look deeper into these. I just wanted to bring it up so that you know the sophistication of the theory that goes behind the processing steps. So we normally will want to just talk about D equal to D naught e to the power delta H over KT. In fact, all the plots that a process engineer is likely to encounter will end up just using this simple expression, and they'll try to find out what is D naught for a particular temperature, for a particular orientation of wafer, and so on, and what is the delta H for that process, okay, for diffusion process. And D naught can be this first part, that is D naught, and delta H is the numerator of this. So here automatically the delta H combines the probability of an atom moving from one point to another, and it also combines the probability of having an empty vacancy formed. So what are the takeaways in this section? The basic model of diffusion process can be modeled by random walk of the constituent entities of a population. Random walk means it can go either left or to the right with a probability of half in our case. Okay, so if that is the case, and there's a distribution, you can actually come up with the diffusion model that we normally encounter. That's a simple way of visualizing what is happening. And what is a summary? Summary is material moves from higher concentration to lower concentration. This is something probably even without knowing about diffusion, talking about diffusion, everybody knows, right? Wherever there is more material and less material, there is tendency, of course, other things being same and there is no potential difference, there is a tendency for things to move from where there is higher concentration to lower concentration. We see that very often unless there are other forces at play. So Fick's first law would capture that part. F is equal to minus D times the slope of concentration. Fick's second law, on the other hand, tells how the concentration evolves over time, and that would depend on the second derivative of the concentration distribution, and that of course, this is assuming D is independent of the position. If it is dependent on the position, you have to go to the more fundamental equation and you have to sort it out. There are situations where you will have to use this thing because the diffusion constant could depend on, for example, the doping concentration that is already present. D could be a function of C itself, right? So such things one encounters and one has to bring it in. Sometimes the effect of electric field will modify, so you'll have to see what it is, and if the electric field varies, then you'll have to have a space variation. So Fick's second law essentially is the more popular version is where D is constant. Diffusion and diffusion constant of atoms in a crystalline lattice, as we saw, instead of having any arbitrary situation where you are talking of some mean free path and things like that, it could be in gases and all that also can be used. If you are going to be more rigorous in a solid, you can approach it by starting in a particular way so that you can develop the model more sophisticated way. You end up getting D is equal to D naught e to the power minus delta H over KT. Delta H is the enthalpy change for the atom go from one position to the other. And here D naught is a complex function of various parameters which takes into account the coordination factor between the 2 points, whether it will tend to come back to its position or it will move on, and then coordination factor, how many pathways are available for an atom in a particular lattice, the Debye frequency of the solid, and the entropy and enthalpy of the motion of the vacancy. Okay. So now we come to the third part of our discussion in this lecture. This is a brief discussion where I have taken some values which will sort of highlight why silicon ended up becoming one of the popular materials, and if you want to choose a new material, what you should watch out for semiconductor processing. So diffusivity value comparison, let us take a quick glimpse of this. Here I will be talking about diffusivity of atoms, primarily diffusivity of atoms in crystalline silicon and also SiO2 to highlight some aspects, and then lattice self diffusion of various elements. This is important. It turns out that if you let things be, even the whole lattice, although all are the same species, you may find that things are moving without any with higher temperature, non-zero temperature, they are moving within the material. So you have to watch out for that. So such materials may not be stable. You might have arranged it in a nice way, but this atom might move to another place and create a vacancy. Over time, such things can happen. So let's start with diffusivity in silicon. This is a very terse plot that I found in Tu Meyer-Feldman's book, which I wanted to share. So this sort of captures the different materials, how they diffuse in silicon. Silicon, if I may say, is one of the most heavily studied material. People seem to know a lot of things about silicon because some of the best minds over the last several decades have studied silicon and various aspects of silicon. So here we are capturing how various elements diffuse in silicon. So let's see what they are. Diffusion constant, as we saw, it follows an Arrhenius principle. This delta E, as we saw, would be the enthalpy, but you can just, for the purpose of our studies, we just say delta E is the energy barrier that it has to cross. Boltzmann constant K and absolute temperature T. D naught is the pre-exponent constant. First order, we take it to be a constant here. Now this plot, if you notice, is plotted with x-axis being 10 to the power 4 divided by T. So reciprocal of T. That means left side is higher temperature, right side is lower temperature. And the normal temperature is plotted here, is shown from 500 to 1300. And as you can see, when you are going to higher temperatures, the diffusion constant D ends up becoming larger and larger. That means higher temperature, you have higher diffusion. This we saw even in the simple case of ink, right? When you use the hot water, it suddenly diffused significantly, right? So same thing with materials. If you go to higher temperatures, most materials diffuse faster. All materials diffuse faster. But then the point is, how fast do they diffuse and how fast do they change in their diffusion? So if you look at it, metals, all these metals, they diffuse very fast in silicon. This is one reason when you go into a fab, they are very particular that you don't carry any metal inside. Sometimes in some fabs, especially where these metals can be detrimental to the device that is being built, BJTs, for example, where lifetime is very important, they prevent you from taking any metals, because any metal that is there will easily diffuse through, and you don't want that to happen. So these metals diffuse fast. So how do you prevent that? You put barriers. We saw that tinitride and other things, which tantalum nitride, those barriers were being used in the case of copper, right? You don't want copper to get into the silicon, so you want to put barriers. That's how you sequester it, prevent it from coming to the silicon. Once it comes into silicon, it can go anywhere and it can wreak havoc, and you don't know where it is going, right? Oxygen and carbon also relatively diffuse faster, okay, but not as bad as metals. But usually these are more benign in comparison to metals, although oxygen also you want to make denuded zones, and we saw that we do that in the initial, after the wafer has been fabricated. On the other hand, this is what is important: group 5 diffuses slower compared to group 3, okay. But what is more important is they diffuse only at temperatures above 800 to 900 degrees. This is why traditionally most processing used to take place at 900 degrees. Today we are coming down to 800 degrees because we want shallower junctions and so on. So you'll find that this is the best part about it, that the dopants are moving, the diffusion constant you can see, the dopants are likely to move only above 800 degrees. In this case here you can see it's about 900 degrees what they have plotted. So that's good. That means that once you have processed it and you bring it to room temperature, which is well below 500 degrees, these things are not going to move at all, okay. So that's the best part about it. So this is the reason silicon technology prospered. The dopants that you have in silicon don't randomly move. They move only when you go take to high temperatures. Another point to note is self-diffusion of silicon. This is very important. Silicon self-diffusion is one of the lowest. Only at very high temperatures it is even showing up, and that too much lower than the other things. This is good news for us. So silicon is a very stable material for making VLSI devices, because once you have put things in place, just because you some high temperature, or high temperature means 100 degrees or so, when chip gets hot, you don't want silicon to move around and create all sorts of problems. So first order, it doesn't do that. That's the reason we choose silicon. We need to choose material which have low self-diffusivity. Let's also take a quick look at diffusivity in SiO2. SiO2, as we have already mentioned, is a key component of VLSI success story, silicon and SiO2. Why? SiO2 can be used as a masking layer, which is what was a popular way in which you could diffuse things and all that. So diffusivity is to be considered if, about 900 degrees if you take, that's when you do the processing, right? We just saw 800, 900 degrees only you do processing. So here the values that are given are for 900 degrees centigrade, as it's written there, and typically for silicon processing, what you find is, if you look at, there are two values you have to look at, D naught as well as the barrier energy. Okay, so if you compare both of them, hydrogen, helium, and sodium can diffuse really fast through SiO2. You have to watch out on this. This is where the mobile ions can play havoc. So, but of course, this is where nitride will come in. Okay, silicon nitride will coming to prevent the sodium from going. H2 and O2 also diffuse through oxide, but that is good for us. That's what helped us do the oxidation of the silicon. We studied that also during the processing, right? Then also note that this is not effective for gold and gallium. So we have to watch out on this. Finally, we talk of lattice self-diffusion. So we could also have lattice self-diffusion within the material. So what it means is, any of the atom that is present within a particular matrix of its own kind can also diffuse. For example, aluminum can diffuse within aluminum, or silicon will diffuse within silicon. How do you track this? One way of tracking this could be you can use an isotope and then you can see where they have moved, and that way you are able to find out whether it has moved from one location to the other. Now, this is an important thing because if you look at it, various materials, the value of d naught and delta H is given here. Lower self diffusion is important because that means the material is stable. If by itself it keeps moving, it can mean that there can be more defects which can be moving, or there can be creep. All these issues can come in. So you want to have materials which do not move by themselves when you have built something. At least during the lifetime of the material, you don't want things to change, right? So if you look at it from those counts, silicon is very interesting. We find that silicon is stable. It has a higher value of d naught, 1460, yes, compared to the others. But what is more important is delta H. Delta H is actually 5.02. So the d value that you will get, which is d naught e to the power minus delta H over kT, that exponential factor will really pull it down because it's 5.02, and if you notice, it's among the highest. If maybe tungsten is a little bit more stable, but typically it's quite high. So that means the actual diffusion value at a particular temperature is very, very low for silicon. Okay, so this makes it very attractive, and that's one of the reasons silicon has been here for quite some time. So what are the takeaways? Diffusivity values comparison that we have done. Significant diffusion of dopants in silicon require temperatures above 800 degrees centigrade. Ensures devices are stable at room temperature. Okay, so most of the processing materials are only diffusing at 800 and above. So room temperature, you can be rest assured they are unlikely to move around. Some metals as well as oxygen, carbon do move around, so you should take appropriate precaution, especially for metals you need barrier layers. Oxygen and carbon, of course, you should keep them as far away from where you want if they are going to interfere with what the device will do. SiO2 is a very good effective mask, and it's useful for highlights the critical role of SiO2 in the success of IC fabrication because it keeps out the dopants. So you are able to use it as a masking layer. SiO2 is not effective to block metals like sodium, and this is where silicon nitride can help, as I mentioned earlier as well. Self-diffusion of silicon is low, and that means the material is thus very stable for building reliable devices. Okay, so with that, we'll conclude today's discussion.